gas exchange lecture. We'll get started. And we'll start off with a definition of internal external respiration. Before we do that, I want to remind us all that we're talking about air, which is the gas. And to think about the gas phase, concentration of gas is given by its partial pressure, because we'll be talking about primarily O2 and CO2 today. Partial pressure. And partial pressure gradients work just like concentration gradients. So in terms of partial pressure, remember that if you have a gas mix in a sealed canister, you're not needing to use real gases. Like for example, if I have red gas, these red balls symbolizing gas molecules, and they're bouncing around in the sealed chamber, exerting a pressure. Well, what if they're mixed up with other gases, say blue dots, and they're bouncing around, adding to the pressure. And the third gas, green, adding even more pressure. The total pressure is what's exerted by all three colors. So the total pressure is a sum of the partial pressure due to the red gas, the blue gas, and the green gas. And if I were just to put numbers to it, I drew 10 dots. So let's say it's a total pressure of 10. 5 is due to the red, 3 to the blue, and 2 would be the partial pressure of green, just kind of using made up stuff. And in terms of gas flow, these pressure gradients work like partial pressure gradients. So each individual gas has a capacity to diffuse or flow from an area of high to low concentration. That's all it is. So when we talk about the partial pressure of real things like the air we breathe, look on the left there. That's a partial pressure breakdown of nitrogen, oxygen, CO2, and water vapor. That's in the air you breathe. Call it atmospheric or sea level air. So imagine that's you living under 1 atmospheric of pressure at sea level. And you're living under a column of air that's really a gas mix, but it's primarily just about 21% O2 and about 79% nitrogen. There's a little bit of water and CO2 that are negligible in the atmospheric air. But what I said prior is that the total pressure of the atmospheric air that you live under, it is about 760. I mean, this pressure is imperceptible. We don't think about the pressure on our body surface. But we do live under an atmosphere of pressure, and to figure out the partial pressure due to each, well, all you do is you multiply, for example, the PO2, the partial pressure just due to oxygen, would be 0.21 times 760, right? And that would give you something like 160 millimeters of mercury if you did the math. And I'm kind of rounding up, rounding to a nice round number. They say 159. And then so if you did the same thing for the partial pressure of nitrogen, it's about 600. Capital P partial pressure due to nitrogen, you just multiply 0.79 times 760 to give you a figure of about 600 millimeters of mercury. And so that's the air you breathe. And what happens is when you inspire this, inspired air is actually different from alveolar air. So if you look at the table, Aspired air is different from alveolar air. Alveolar air, I would focus on the PO2 and the PCO2, 104.40. Ignore the other things. And the alveolar air, underline it twice, is what's important because that is what is available for gas exchange in the alveolar space for external respiration. So that's what's important, not so much this. But this is what the air you actually breathe, and it changes because it's mixing with the air already in the conducting airways. There's a lot of water vapor that has a dilution effect on things. Well, in the end, pay attention. PO2 is about 104 millimeters of mercury. The partial pressure due to CO2 is about 40. And those are the numbers that are desirable so you can have proper gas exchange at the lung. Now, what we learned before is that the system uses a circulatory system to make exchanges and then circulate these blood gases to the peripheral tissues down at the bottom. All right, so let's go through this. So imagine this is one big alveolar space. You breathe in air, you breathe out air. But the whole point of breathing in and out is to keep this at 104.40. And it doesn't really fluctuate very much. But what we see from this is blood coming in. It's oxygen poor and CO2 rich. Now, the numbers I want to give you for that is PO2 40, PCO2 45. So these are our quote-unquote oxygen rich and poor numbers. And if I don't put units of millimeters of mercury, it's understood. So 40 and 45 are 40 millimeters of mercury and 45 units of mercury. And that's the blood coming in that the right heart pumps to the lungs. So these are the numbers here. What they're going to do is equilibrate with the alveolar air. Remember, partial pressure gradients are just like concentration gradients. So if PO2 coming in is 40 and it equilibrates with 104, what's the gradient? The gradient is blood picks up the O2. It's going to equilibrate with this oxygen poor blood. This is oxygen rich, the alveolar spaces, and the pulmonary blood is oxygen poor. So O2 enters the blood. Blood leaving is oxygen rich. Maybe it equilibrates almost to 104. They say pulmonary veins collect blood at about 100. Fine, 100. The numbers may change a little bit. Maybe it's 104, maybe it's 103, maybe it's 100. But the point is, it's definitely not 40. You've picked up oxygen. Okay. The other thing is the CO2 that leaves. It's not a very steep gradient, but high to low. CO2 leaves, and that's kind of like a waste product that you breathe off. Breathe off the CO2. We call this the external respiration, the gas exchange at the lung. External respiration. So that blood leaving, instead of being 40, 45, is 100 and then 40 for oxygen and CO2 respectively. And that's the blood that the left heart pumps to the rest of the body. If you look at the bottom where it says tissues, let's say you have some tissues there, some moil cells, that are utilizing oxygen. And if they're utilizing oxygen, oxygen is becoming lower. And so maybe the PO2 is 40 millimeters of mercury, or less than that, depending on the conditions. Maybe the partial pressure of CO2 is 45 millimeters of mercury or greater. So this needs blood supply. Okay, it's going to get it by the systemic capillaries. So blood coming in is our same numbers. I'm not going to change them. PO2 100, PCO2 40. Oops. PO2, PCO2. And then you're going to make exchanges with the peripheral tissues. The blood will deliver O2, drop it off. And it'll pick up CO2, which is considered a metabolic waste product. You exchange in reverse, and so then blood leaving is PO2 40, PCO2 45. And we're back where we started. This is the blood that's conducted by systemic veins and delivered back to the right heart to pump to the lungs to reoxygenate. So those are the numbers, the partial pressure numbers. I always put this here to remind me to kind of talk about FRC. It's very important that you understand that these numbers in the lung stay steady for the external respiration. Not to be confused with the gas exchange here, which is called internal respiration. We say this is gas exchange at the lung, this is gas exchange at the tissues, or peripheral tissues, just any old tissue in the body. But this is definitely the lung, right? The alveolar space. Now, you know that you breathe in and out, and you measured all the lung volumes and capacities, and you kind of live here in the tidal volume. Of course, you can take a super deep breath like you did for the vital capacity, but we mostly live here in the tidal volume. And all of your reserve right here is called the FRC. Think of the FRC as a big mixing chamber. The goal of this slide is to teach you how these numbers stay steady state. They don't fluctuate every time you take a breath in, every time you take a breath out. That would not be good. If these fluctuated, your blood gases would fluctuate, and that's not good for cell metabolism. They need steady state. So these numbers remain steady state. FRC ensures this. FRC is a big mixing chamber that keeps these keeps these values steady state. You're not removing all the air every time you take a breath out and then restoring it every time you take a breath in. You have this big 2.5 liters of FRC. Now you even measured this blue volume. What is it? Identify, just from here to there. ERV. What about the green? That's RV. Now, to define FRC, it's ERV plus RV. But what's its function? Its function is shown here. So note this slide. You're expected to know these 4 reasons here. In the absence of FRC, there would be fluctuations of O2, CO2 during tidal volume, inspiration, expiration, in alveolar air, and in pulmonary blood. So that's what happens if you did not have FRC. But with FRC, during inspiration, FRC buffers a big increase in O2 and pulmonary blood. But we don't like that. We don't like big changes. A buffer doesn't prevent change. It just minimizes the change. So when you take a deep breath in, you're delivering the O2, but this big mixing chamber kind of buffers a big jump. The same thing when you take a breath out. During inspiration, Same thing for CO2 when you take a breath in. During inspiration, FRC provides a reservoir for CO2 mixing. In other words, you can still deliver CO2 to the alveolus during taking a breath in. That's supposed to be counterintuitive. You think, I only breathe off CO2 when I breathe out. How can I get rid of it when I'm breathing in? Because you're not breathing it out, but the blood is dumping it into FRC. You're just breathing up and down up here, but this big mixing chamber, the blood flowing by, regardless if you're breathing in or breathing out, can still dump it into this space. Okay? And that's very important for these steady state values. And consider number 3 and 4. And during a breath out, FRC buffers a big decrease in CO2 in the pulmonary blood. And also during taking a breath out, during expiration, FRC provides an O2-rich reservoir. You can still deliver O2 from the alveolus to the pulmonary blood during a breath out. So even though you're breathing out, O2 is still entering the blood. I mean, it's something you can't see, but it does happen. So that's the function of FRC. Note that slide. You're going to have to understand the function of it, because FRC is that buffer. We ventilate to keep the partial pressures at around a steady state of 104.40. So those are the numbers that we usually report. We don't report a set of numbers for inspiration and a set of numbers for expiration. We don't do that. It's just these are the numbers. FRC ensures that we pretty much stay like that. So if you're ventilating, we have to couple it to proper blood flow or perfusion. So these things are coupled. You know, air goes in and out, right? And blood goes round. Blood goes round and round. It's going to keep circulating whether or not you're breathing. So these two things operate pretty much independent of each other, but they work together. Just to prove it to you that they're independent, I could hold my breath, but blood is still flowing because I could feel my pulse. Okay, my heart doesn't stop when I hold my breath. Well, let me kind of illustrate that. Well, what would happen if I held my breath in this picture here? Put a stopper in it. Hold breath. Well, eventually, if you held your breath, this gas exchange would stop really quick. Fresh air ain't coming in, but blood keeps going round and round. So the blood coming in is 40-45. Eventually, this will equilibrate with that, because this is not being renewed, and that keeps coming in 40-45. So eventually, these numbers will change to 40-45, and eventually, the blood leaving the lungs, coming back to the left heart, will be 40-45. Okay, so that's why you need proper ventilation, perfusion coupling. I mean, that's an extreme example, holding your breath, but it's a lot more finely tuned than that. The basic idea here is, think about it. You ventilate to keep fresh air coming in. You inspire air to make sure the CO2 levels, you inspire air to make sure the O2 levels stay up, and you expire to eliminate the CO2. The blood flow, the perfusion always refers to just the blood flowing. The goal is to take away that O2 and to dump the CO2. So they have to work together. You inspire air to keep oxygen high. You want to take that away in the blood. Okay. You deliver the O2 to the alveolar space so you can breathe it off. So to keep that tightly coupled, I gave the hold your breath example. Let's look at this figure here. Look at how the body regulates it when there's a mismatch in ventilation to perfusion. breathing, perfusion, with blood. That's the blood flow. They're coupled. You can avoid mismatches. Okay, look at the left. That's a mismatch. That's trying to show you the alveolus is underventilated and overperfused. That's a mismatch. Underventilated, overperfused. If it's underventilated, there's not enough oxygen getting in there, so low PO2, and CO2 is accumulating. High partial pressure due to CO2. Well, you don't want to perfuse that. Remember what the function is. The function is to get oxygen into the bloodstream and dump the CO2. But if it's underventilated, if that's the alveolar air, you don't want to perfuse that. Okay? So you constrict. You constrict the pulmonary arterioles. By doing that, you restrict blood flow. So now at least you're matched. It's like now you're underventilated and underperfused. You match it. Don't send the blood flow to this one. It's underventilated. Send it somewhere else where it's better ventilated. That's all. It's like just a rerouting of blood to where it's most ventilated, because that's the job of this system, to pick up the O2 and then dump the CO2 into the alveolar space. So don't so much perfuse that one. This one will be better. Okay. So for example, this one, they tell you that this is a mismatch, but it's in reverse. Now it's overventilated, underperfused. Now it's like there's plenty of oxygen, elevated PO2, and decreased CO2. So this is a good place to perfuse. You have plenty of way, plenty of O2 to take away. You have a nice gradient to dump the CO2. So then you dilate. So now it's matched. It's overventilated, overperfused. And this is the reverse of what I taught you before. What I taught you before for blood flow, that if tissues get hypoxic, you dilate to prevent ischemia. That's how it normally works everywhere else in the body. But remember, in the lungs, it's the reverse. Everywhere else in the body, the goal is to deliver the O2. So that's why everywhere else you would dilate when it's hypoxic. But here, because it's reversed, you're trying to pick it up, you do the reverse. You restrict the blood flow where it's hypoxic, and you dilate where it's overventilated, where there's plenty of oxygen, because you're trying to pick it up. So breathing, ventilation, blood flow, perfusion is coupled. The next question I have for you is, well, how long does this equilibration take? When blood flows by, it picks up the O2, dumps the CO2, comes in oxygen poor, leaves oxygen rich. This exchange takes about a quarter second. It only takes a 0.25 seconds to equilibrate. The transit time is about 0.75 seconds, and so it does it in plenty of time. Right? You're able to equilibrate that quickly for the O2. And for the CO2, I put them both on. They put them both on this figure, so I included it. I don't like this figure because they only show the exchange of one gas. They don't show the exchange of the CO2, but it is shown here. What they show here is blood coming in at 40-46, okay, PO2 40, PCO2 46. Not 45, 46, okay? They changed it a little. But they show the pulmonary capillary completely enveloping the alveolar space, which is a little more accurate. There they have 103.40 on the inside of the alveolar space. You make your exchanges, blood leaves 103.40, okay? So the exchanges happen quickly, it equilibrates within a quarter second. All right, so now that you have gas exchange at the lung, transport of oxygen and CO2, I want to talk about that next. You use the bloodstream to transport the blood gases over long distances, but how are they transported in the blood? Let's remember that the air we breathe is a gas, but the blood that transported is a liquid. In the liquid phase, such as blood plasma, the concentration of O2, CO2 gases are given by their partial pressures, 104 and 40 in systemic arterial blood. So all the blood that's transported is a sum of the gas molecules dissolved in the plasma, but also that is chemically reacted or combined. So this number one, this dissolved part, that's our partial pressure. Okay, that's like carbonating your soda pop. You apply pressure and you push the CO2 to bubble in to make your beverage fizzy. Okay, that's why fizzy drinks taste fizzy. You're tasting the gas in there fizzing. It gives it that sensation in your mouth. And that's why when your drink goes flat, there's no fizz because all the gas has escaped. So, you know, one way is we just bubble the gases in, that gives a partial pressure. And the other, more significantly, we chemically combine and react our gases to different things. So let me kind of go through that. Arterial O2 content. So O2 in the blood, 100% of it can be given by this number, 20 mils O2 per deciliter of blood. That's about the content of it. However, it breaks down in a couple of different ways. That O2 is transported, it's either just dissolved in the blood, just like gas in a soda pop. We call that dissolve. Turns out that's only 1.5% of 100%. That dissolved state is our PO2 of 104. Our partial pressure of 104 millimeters of mercury. It turns out it's actually a very small percentage of how blood is transported in arterial blood. So it's only about 0.3%, or no, not percent, 0.3 mils O2 per deciliter of blood. The other 98.5% is actually bound to hemoglobin. 98.5% bound to HB. Remember we call that oxyhemoglobin, HbO2. So that's the other 19.7, about 19.7 mils O2 per deciliter of blood. All right, so that's how it breaks down. It's either dissolved or chemically bound to hemoglobin for the oxygen. And for the CO2, the numbers are different. 100% is about 60 mils CO2 per deciliter of blood. And it's transported in 3 different ways. A small percentage is dissolved, just bubbled in like soda pop. It's about 7%. So that's about 5 mils CO2 per deciliter of blood. About 23% is bound to hemoglobin, HbCO2. That's called carbaminohemoglobin. So that's about 15 mils of CO2 per deciliter of blood. The majority of CO2 is transported in the form of bicarbonate, so about 70%. Bicarbonate is HCO3, full negative charge. Bicarbonate. So that's the rest. It's about 40 mils CO2 per deciliter of blood. Right, so that's how the numbers break down. Hold on a second. Okay, let's focus first on O2. At the start of today's lecture, I really hammered number 1. The dissolved state gives us our PO2 of 104. And it's the same thing for the PCO2. That dissolved is our partial pressure CO2 of 40 millimeters of mercury. Okay, that's just the dissolved one. When something is chemically bound or chemically reacted, it cannot exert a pressure. Okay? That's why the dissolved only refers to the partial pressure. In terms of oxygen, it's like, oh, why do you keep mentioning this? It's such a small proportion of how it's transported. Actually, it turns out it's really important. This small amount is really important. But yeah, in terms of sheer quantity, most of your oxygen is bound to hemoglobin. It's like 98.5% of it. But let's pretend for a second, you didn't, let's pretend you didn't have hemoglobin. That your blood wasn't red, it was yellow, and you just had the plasma. What happens then? Well, then you breathe, you keep a PO2 of about 100 in the alveolar space. All it can do is equilibrate, so then you get a PO2 of 100 in the blood. So then that's only our 0.3. This figure says it's 3 because they use liters instead of deciliters like I did, so it's off by a factor of 10, but it's the same thing. Okay? But this isn't nearly enough to satisfy our metabolic needs. With hemoglobin, you get about the 19.7 bound to hemoglobin, and I like how they illustrate hemoglobin in this figure. Here's this. Here's hemoglobin as a circle 4 square. And there's 1 hemoglobin combined 4 O2. So pretend O2 is a red dot, and if it binds hemoglobin, there's all 4 spaces occupied. It could potentially bind 4, and if they're all bound, we say that hemoglobin is saturated, 100%. HB saturation 100% because all 4 spaces are occupied. They draw one where it's like on that figure where they leave it empty. So what's the saturation here? 75%. And so that's the idea of saturation. How many of those available places are taken? So, oxygen transport, two mechanisms: dissolved, bound to hemoglobin. Obviously, the bound to hemoglobin part is more important because that's most of the oxygen in our blood. But that little small dissolved amount, super important. Hemoglobin saturation is the most important way oxygen is transported. We want hemoglobin to be saturated when it leaves the lung. But what determines that? It actually is the PO2, the dissolved part. The PO2 determines the saturation. Okay, so we want the oxygen tension to be high, 104. That increases the saturation of hemoglobin. It's actually a near 100% saturation if the PO2 is high enough in the alveolar area. And so, so the idea is when you plot one against the other, say PO2 on this axis, sometimes we call it oxygen tension. We plot it against hemoglobin saturation as a percentage and just graph it against each other. The concept is if the partial pressure of O2 is low, saturation will be low. It will be hardly saturated. It won't bind the oxygen. And what we learn is that if oxygen tension is high, well, saturation will be high. Okay. And well, the question becomes, how does it change from low to high? And instinctively, you might think it's a linear relationship, but I wouldn't draw this straight line because that's not the case. It's kind of like that. So look at that curve. That's what it really is. Is that a straight line from low to high? No, we describe that as sigmoid shape. So it's not straight, it's not truly strictly a linear relationship. It's kind of more, when it's high, it kind of stays high, and then it kind of drops off real quick, and then kind of like that. It's a sigmoid shaped curve, that's shaped. Oxygen, O2, hemoglobin, saturation curve is sigmoid shape. I have it labeled properly on the slide there. We said that there's a plateau, that there's a steep slope. So this is the relationship. That PO2, that dissolved state, we want it high where we're breathing, right? And we wanted a lot of oxygen, and it turns out at sea level, the air we breathe here, for example, in Sacramento, the PO2 is about 100. And at 100, let's read it right off the table, the saturation level is almost 100%, 97.5% saturated. But let's say you kind of like, remember I drew that little stick figure under an atmosphere of air? Okay. Think conceptually with me. You're at sea level. What happens if you go to like somewhere that's actually below sea level, like Death Valley? And theoretically, I guess you have more air on top of you. maybe the total pressure is not 760. Maybe it's, well, would it be more or less? It'd be more. It'd be like maybe 770 millimeters of mercury, say in Death Valley, California. Or you live below sea level. Or what if you went up higher, or it's high altitude, and you have less air above you? The number theoretically should get less than 760. Okay. And well, when the air gets thinner, when you go to altitude, like for example, I looked it up, at around 12,000 feet, PO2 is about 50. And here's some like high, this is kind of put it in reference, some of the highest peaks in California are around that range. But anyways, it's really low. So it's like at a PO2 of 50, it turns out you're actually still pretty well saturated at about 83.5%. So even though we've halved it from 100 to 50, the saturation isn't cut in half. It's actually remaining pretty high. So this is actually a good thing, and we call this part of the curve, where it remains relatively flat to plateau, and this is really good for the external respiration. And we're trying to saturate the HB. Plateau. Good for external respiration.
Professor, is the second figure with the 83.5%, is that for the low altitude or the below sea level?
50 is for the 12,000 feet.
So that's
high altitude.
Okay,
Yeah, altitude. So on this one, so I'll erase this. So the terms are sea level and altitude. Okay, that's sea level. This is altitude. You know, high up in the mountains. For some reason, they don't use the terms high altitude, low altitude. They say sea level, altitude. That's it. Altitude, you're on the mountain. Sea level is, well, like living here. Okay, so yeah, this is good for external respiration. The air you breathe, you know, even if it gets down to 50, you're still relatively saturated. So in the lungs, the hemoglobin is pretty well saturated, 83.5%. And then you have the big drop-off called the steep slope. And that's good for internal respiration. Steep slope, good for internal respiration. Like for example, at a PO2 of 40, saturation is 75%. So remember that number, PO240, it was from a prior slide. Let me go back for a second. This slide. Look at the tissues. We said it's 40, or less than 40. Okay? So what we learned is, when blood flows to the tissues and it encounters an oxygen tension of 40, it's 75% saturated. So when it comes in, maybe it's nearly 100% saturated because it came from the lungs and it circulated. So what happens when it gets to the tissues and it encounters a lower oxygen tension, a lower PO2? How many get off? One. Very good. Boop. and that goes to the tissues, okay? And of course, it could be less than 40. Maybe you're vigorously swimming, working out, whatever, and you use more oxygen and you're utilizing more and more and more oxygen. Maybe the oxygen tension in the working muscles gets to 20. And at this point, we're in the steep slope, so it's more efficient at dropping it off. Let me go back to the oxygen tension saturation curve. At 20, saturation is 35%. So you cut the oxygen tension in half, and saturation is way less, basically. Well, you can see the numbers. You're more efficient at dropping it off. Okay, so that's good for internal respiration because the tissues need the oxygen. All right, so the sigmoid-shaped curve, it's kind of beneficial for both types of gas exchange. Now this figure, it's kind of hard to read, but I kind of liked how they put the hemoglobin potentially binding 4 oxygen molecules. And they call that 100% saturated, 75, 50, 25, 0. Okay, and they associate that with that curve. Let's see here. All right, this is a good spot to take a break. We'll talk about some other factors that affect the saturation curve.